All right, let me describe the experiment, which is a micrometer. Micrometer is also called a screw gauge. It's also called a screw gauge. And the principle of operation of a micrometer, now this is a micrometer. That is what we'll be using, and this is called a micrometer. Now, the principle of operation of this micrometer is a screw. Now, you can see these threads on a screw. These are the threads on a screw. The distance from one thread to the next thread is called a pitch. The distance from one thread to the next thread, or the space between threads, is called a pitch. Now, if you take a screw and if you turn a screw clockwise once completely, how far does the screw move? The screw moves through a one thread space, which is basically a pitch. So when you turn the screw clockwise once, the screw advances by one pitch. So that's the idea of a screw. Now, the screw gauge also is a screw. You can see that this is a screw that comes off. It's a big screw that comes off, and you can see this coming off. You don't have to take it off when you operate it. See, that's a screw. And the threads are inside here. And this is a nut. And so the screw goes into the nut. It's a specially shaped screw. It goes into the nut in this fashion. And there comes the screw. Goes a long way. The pitch of this screw is very, very fine. That's why it is taking so much time to move little by little by little. So how far does this screw move for every one turn I make? Okay, how far does this screw move for every one turn I make? It is 0.5 millimeters. So if I take the screw from this position, if I take the screw, if I turn it once completely backward, now by the way, this is a lock. You have to keep the lock always unlocked. If it is kept like this, then it won't move. So keep it unlocked, and then you can move it. So if I turn the screw once completely backward, how far did this screw move? This gap over here that you see, the tiny gap, that is called a pitch. So that is a pitch of the screw. If I turn it once, it moves by 0.5 millimeters. If I turn it again, it moves by one more 0.5 millimeters. So right now the gap is 1 millimeter. If I turn it again, the gap is 1.5 millimeters. Okay, so how is this micrometer or the screw gauge able to give us more precise readings than a vernier caliper? Let's look at it this way. So what did I say is a pitch? Pitch of the screw is how far the screw moves in one turn. And I turn this once completely, how far does it move? That's called the pitch. The distance moved over here is called the pitch of the screw. Okay, so here we go. This is one full turn. And the gap here is 0.5 millimeters. So what's the smallest gap that I can create over here? If you noticed, on this scale, which is a drum, you can see there are 50 divisions marked over here. 0, 5, 10, 15, 20, 25, 30, 35, 40, like that, till 50. There are 50 divisions on this drum. This drum, by the way, is called the thimble. This is called the thimble. And this scale that you see inside here is called the pitch scale. The scale that you see here is called the pitch scale. I don't know if you can see it from there. That is called the pitch scale. The scale that is here is called the pitch scale. And this is the thimble. We can also call it head scale. So the thimble contains the head scale division. There are 50 divisions. So the pitch is 0.5 millimeters. Pitch is 0.5 millimeters. And if I turn the screw backward once completely, which is through 50 divisions, the space that you see here is 0.5 millimeters. So therefore, what's the smallest gap that you can create here? The smallest gap that you can create there is by turning it by one division. If you turn it by one division, that is called, this is another micrometer. It's apparently better. So you can see the 0. I don't know if you can see, that is a pitch scale 0, and that is the head scale 0. Right now it's coinciding. See, it coincides perfectly. So if I turn it once completely backward like that, if I turn it once completely backward, 45, 0 back again. So if I turn it once completely backward, the space that you see over here, that is 0.5 millimeters. So if 0.5 millimeters is the movement of the screw for 50 divisions, what is for one division? For one division, it will be 0.5 divided by 50, which is 0.01 millimeter. That is the smallest that this instrument that can give you. And that is printed over here as well. You can't see it clearly here. You can see on this, it says clearly 0.01 millimeter. So the smallest reading that this instrument can give us is 0.01 millimeter. Remember, for a vernier caliper it was 0.1 millimeter. And for a meter stick, this is for a micrometer. For vernier caliper it was 0.1 millimeter. For a meter stick it was 1 millimeter. So this is able to get you up to 1/100th of a millimeter precision. So the idea of the micrometer is understood. Now some of the features of the micrometer. So how exactly are we going to take the readings? So if you want to know, oh, by the way, before we start with it, I have to tell you, okay, this is a lock. It's locked, so it won't move. Unlocked, so keep it in the unlocked position when you move it. Now when you unscrew it, you can use the thimble and turn it back. But when you try to tighten it, never use this thimble. Use this thing which is called a ratchet. This is a ratchet. You can see that the ratchet, you keep turning the ratchet, you can see it stops and it won't turn any further. So as soon as the right pressure is applied over here, the micrometer, the ratchet will stop turning it. That is basically to protect this micrometer. Now if you turn it by using the thimble, you'll keep on twisting and turning and this can break. So the ratchet is something that you should use when you're tightening the object. So right now there is nothing in this space. If I turn it once completely backward like that, the space here is 0.5 millimeters. If I turn it again one more time, the space is 1 millimeter. If I turn it one more time, the space is 1.5 millimeters. You should be able to read it from the pitch scale, which is right there. But it's a difficult thing to read. Okay. Now, so you know what is thimble? This is a thimble. This is a ratchet. And the smallest reading that this can give you is 0.01 millimeters. Okay, now how do we use this instrument? To use this instrument, this is how it goes. Let's say, for example, I want to find the diameter of this metal. I want to find the diameter of this metal. Okay, so to find the diameter of the metal, the best way to do is to turn it every time by known measurements like this. I turn it once backward completely. The space over here is 0.5 millimeters. Will it fit in? This will definitely not fit there. It will not fit in this space. It will not fit there. So I turn it again a second time. So now the space is 1 millimeter. It won't fit in. I turn it again. It is 1.5 millimeters. That's not fitting in. I turn it once again. And now the space is 2 millimeters. Let's see if it fits in. It's not fitting in. Now I turn it again. Now it's 2.5 millimeters right there, and it's not fitting in. I turn it once again. Now it is 3 millimeters, and it fits in. So when it is 3 millimeters, it's fitting in. But when it was 2.5 millimeters, it was not fitting in. So what does it mean? That means the diameter of this metal is between 2.5 and 3, because when I put 2.5, it was not fitting. When I put 3, it was fitting. So the pitch scale reading, okay, is going to be equal to 2.5, the smaller one, because it is between 2.5 and 3. So now what you do, keep this object in place. Keeping this object in place, see, it's right there. Keeping this object in that space, use a ratchet and turn it in. And when it clicks, you're going to take the reading from here. So what reading do you see over here? I see the 48th division coinciding. 48 is coinciding. Now, what do you mean by 48? 48 of this. So, this is a pitch scale reading. Then the head scale coincidence is 48. There it is. And then the head scale reading is 48 times 0.01, which is 0.48. So what's the total reading? The total reading is 2.5 plus 0.48, which is 2.98 millimeters. That's how you take the readings using this instrument. Okay, so how are we going to what are we going to do with this instrument? We're going to do a couple of measurements. You'll be given some pieces of glass, so you can measure the thickness of glass. You can measure the thickness of this paper. You can measure the thickness of wires, diameter of wires. And so you'll be given a set of items to be measured. So you're just basically going to do those measurements. So what kind of a table are you going to make? The table that we're going to make is this. Here's the table. This is the object. And here comes the pitch scale reading. Then you have the head scale coincidence. And then you have the head scale reading. And you have the total reading. And you have the average. Now, pitch scale reading is going to be in millimeters. Now, you remember when we did vernier calipers, this was all in centimeters. Now, this is all going to be in millimeters. So, pitch scale reading is in millimeters. Head scale division, head scale coincidence, no. Head scale coincidence, there's no unit for it. Head scale reading is going to be in millimeters. Total reading is going to be in millimeters. Average reading is going to be in millimeters. So everything you're going to measure is in millimeters. Now, what is the objective? You're going to do some diameters. So if I say, okay, diameter of copper wire. So if I give you a piece of wire and you're supposed to measure the diameter of that wire, you measure the diameter of the wire in the same manner as you do it here. So again, if you turn it once, the distance mode is one pitch. If you turn it 2 times, it'll be 2 pitches. Now this one says I moved it 5 times. After I moved it 5 times, the distance is 2.5 millimeters and it is not fitting. It is not fitting. So when I moved it 6 turns, that is totally 3 millimeters, then it fit. So pitch scale reading is the lower one of the two. So 2.5 to 3. So you take the lower one and put it as a pitch scale reading. So this will be 2.5. Head scale coincidence is the line that matches up. The line that matches up here and that we write here. Head scale reading is 0.48 and the total reading is 2.98. And you repeat it 3 times, 2.5. The next time you got 47, so it's 0.47 and it's 2.97. Do it again at some other location, you'll get that. And then 0.46, 2.96. Then you take the average of all this and you get 2.97 millimeters. And then you go ahead for the next measurement, which will be probably the thickness of glass. Thickness of glass. Do the same thing. Thickness of paper. How do you measure the thickness of paper? To measure the thickness of paper, what you do is you take this paper and fold it once. Okay, I'll show it on this paper. You take a paper and fold it once. So when you fold it once, how many thicknesses of number of thickness is 2. Fold it again. Now the number of thicknesses is 4. So when it is 4 thicknesses, you insert this into the micrometer. You insert it into the micrometer. So you turn the micrometer once and then try to fit it in. Try to fit it into the space and see if it goes. Yeah, it goes. So you fit it in and then turn this back. So you fit this in and then turn it and you can see the coincidence. This is what you do to measure the thickness of paper. Now remember, when you measure the thickness of paper, you measured for 4 thicknesses. So what you write over here is thickness of paper, 4 thicknesses. And then you get the average. Then what you do, you divide that with 4 to get the thickness of paper. Alright, so you'll be given some of these as objectives and all you do is just do those measurements. And then after that you measure the length of paper in millimeters and then width of paper in millimeters and the thickness of paper from here you can get. This is thickness is equal to whatever reading you get divided by 4. Okay, whatever reading you have here divided by 4, that will give you thickness in millimeters. So get the length in millimeters, width in millimeters, and then you can get the volume of paper equal to this length times width times thickness. So you get so many millimeter cube, and then you can find the mass, determine the mass of paper, and then find the density of paper. So the density of paper is going to be, you measure it in grams, so you can say grams per millimeter cube. You can do that. Or you can express it in grams per centimeter cube, but you can leave it in gram per millimeter cube. You can find the density and put it down there. So that will be your experiment. Alright, so when you get this instrument, handle with care. This is a ratchet. You're supposed to use a ratchet, and it may be a little difficult to take the readings from this point, so make sure that you understand this point. When you turn this micrometer once completely, the space here is 0.5 millimeters, which is called the pitch. Okay. All right. So you got the format of the table, and this is pretty much what you're going to do as measurements, and make a lab report with all the details as I have mentioned earlier. I'll read them once again. All the details that you need. Number one, aim. You need the aim of the experiment. Okay, it's title here, and your name and all those things here. Aim, material used. Then theory. Write down the theory as to how this instrument is able to do the measurements properly. And then the formula used. The only formula we use over here is density. Density is mass over volume. And then after formula used is procedure. Procedure. So procedure lists all the different steps that you take to get those measurements done. And after procedure comes observation. That's where we have the tables. That's the observation. Make sure you write all the units on the top. Okay, missing units means you lose points. Observation. And then comes calculation. The only calculation you're going to do here is a density calculation for the paper. So make sure you show the volume and then the density. And after calculation comes precaution. So what are things that you should take care, like zeroing the scale and then using the ratchet instead of the thimble. So instead of the thimble, use a ratchet to protect the material that you're putting there and to protect the micrometer. And write any other precaution that you might need to write here, and then the conclusion. So this conclusion. So all these points are required in the lab report. Okay. If any of these are missing, then you're not going to be getting the points. Make sure the units are mentioned wherever you do any calculation or data taking. All right. Good luck with the lab. Oh, I forgot to mention about one point, which is a very important point. So some micrometers have error. Now can you see the zero over here? The zero here matches perfectly with this line, which means this one has no error. Okay, hope you're able to see it. See, the zero matches perfectly with this. So there's no error. Now on some micrometers, you will see something like this. So this means, if you look at it carefully, you can see the third division is coinciding. So without any object over here, if you click it, it's not matching with 0, it's matching with number 3. And what does that mean? 3 divisions are excess. On this faulty micrometer, 3 divisions are already shown in excess. So what you have to do then is, after you finish all your readings, once you get 2.97, you have to knock off those 3 divisions from there. Now 3 divisions is equal to what? 3 divisions means 0.03. So knock off 0.03 from here. And that is one correction that you're supposed to do. Now it's called the zero error. So you have to take care of the zero error. So if zero error is positive, which means like division 3 or 4 or 5 or 6 coinciding. Those are positive errors, and what you need to do is subtract error from average measurement. Subtract the error from the average measurement. For example, if it was something like this, the third division is matching. So the third division matching, the error is plus 0.03 millimeters. So what you need to do is take this off from the average. So the average is 2.97 millimeters. So applying this error, take off this error from here. So corrected average is 2.94 millimeters because you're taking that off from here. So this is what we need to do if it is a positive error. Now you can also have, if zero error is negative, how can you have a negative error? Here is typically one with the negative error. See? Again, I don't know if you can see it. Yeah, there it is. You can see there, when this matches, it's a 45th division matching. You can see the 45th division is matching. So if it is 45th division matching, how many divisions behind the zero is that? It is 5 divisions behind the zero. See, that's a 0. It's 5 divisions behind the 0. And so if it is like 45 coincidence, then it's 5 divisions below. So the error is minus 0.05. So what do you do for corrections? Corrected average will be 2.97 plus, you have to change it to plus 0.05. So the answer will be 3.02. So you can see how the correction is done. That is if you have an error. Some of the micrometers have errors. So when you just close this ratchet in, the error is already indicated there. All right. So just take care of the errors. You can ask me questions if you don't understand some of those in class.